In the past lesson, I introduced the Schrödinger equation, which gives us the wave function psi, x, and t. But a particle is localized at a point, whereas the wave function, as its name suggests, is spread out in space. This means that for a given time, t, it is a function of x. Remember that psi in general is a function of x and t. But if we fix t, it is still a function of x. Therefore, the wave function is spread out in space. Worse than this, psi in general is complex. So, how can such an object represent the state of a particle? Remember that in quantum mechanics we have wave particles The wave particles sometimes show wave-like features and sometimes demonstrate particle-like features. So psi should be suitable for both pictures. The wave function itself has no physical meaning because it can be a complex number or a complex function which is not real. But Max Born provided a statistical interpretation for psi star psi, as I defined here. So statistical interpretation for this quantity psi star psi. Psi star is the complex conjugate of psi. We show this quantity by this notation, absolute value of psi squared. This quantity is not equal to psi 2. So in quantum mechanics, we should always be careful not to confuse these two things. Psi 2 is correct when our function is real, but when we have a complex function, we should take its complex conjugate and multiply it by the function itself. So in our case, I have multiplied psi star times psi. The Max Born interpret the product of psi star and psi as follows. Psi, x and t squared, which is equal to psi star, let me correct this, times dx, which is psi star x and t psi x and t dx. This is the probability of finding the particle between x and x plus dx at time t. For an interval, for example, between a and b, I can write an integral like this, integral from a to b, psi x and t absolute value squared dx is the probability of finding the particle between A and B. So if we draw psi, absolute value of psi squared versus x, then the probability is the area under the graph. For example, consider this graph. The y-axis is psi squared and the vertical axis, horizontal axis is x. So for example, consider this example. Suppose this is point A and this is point B. Then the probability of finding the particle between A and B is this area, which is shown by green color. It is clear that the total area from minus infinity to plus infinity is equal to 1 because we are sure that the particle is somewhere in this interval. So this means that integral from negative infinity to positive infinity psi squared dx is equal to 1. We will discuss this later, which is called the normalization of the wave function.